So, hi everyone. We have discussed in last session, today we will talk about something called homeomorphism. Although I have already defined it and given you the motivation for it in the very first, lecture, that we want to see, we want to give a structure to a set that we have already given. That is what topology is. And then we want to see when of these structures are same. So let me, proceed by a definition, by or three definitions. Then, we will see various examples and properties. So definitions. So let us fix a convention. Let X and Y be topological spaces and f from X to Y be a function. So we have this. So number one, we say F is a homeomorphism. So in groups, you might have seen isomorphism, right? Iso means similar, morphism means structure. So homeomorphism is also like same structure. So what a group isomorphism does is, or a vector space isomorphism does is, it preserves your linear structure, right? So something similar here will happen. And you may have seen various things. If two vector spaces, for example, are isomorphic, then what about their dimensions? If they're finite dimensional spaces, then their dimension should match, right? So, like this, if you are aware of metric spaces, similarly, we will see, various properties which is preserved under such map, which we call homeomorphism. So that's what we have, a structure, we have a map. So what is a homeomorphism? We say F is a homeomorphism if number one, F is continuous. Number two, F inverse exists and F inverse is also continuous. So these are the two conditions effectively we want. So in sets, we say two sets are equivalent if there is a bijection between them. Here, since we are dealing with now topological spaces, it is not just merely a bijection, the both map and its inverse should be continuous also. And in this case, we say X is homeomorphic to Y. So this is the symbol. X is homeomorphic to Y. Or F is a homeomorphism between X and Y. I hope this is clear. So basically, if I have a homeomorphism between two topological spaces, those are same for me in the, if you know the category, in the category of topological spaces, or if you don't know it, in the collection of topological spaces. So you can prove that homeomorphism, this property, two spaces being homeomorphic, okay, so homeomorphism is an equivalence relation. Okay, we will see examples. Let me define two more definitions. We say F is a sorry closed map if can you guys guess if f of f is closed where in y for all f which are closed in x. Similarly, the other definition is open map. If f of u is open in y for every u open in x. You may be thinking why these two definitions now, right? So before going on to, examples, let me do one proposition. Then, we will see some examples, at least two examples. So let me have a proposition. Position. Sorry. I think spelling I was writing right only. If there is spelling mistake, forgive me for that. So you have f from x to y be let me see what all you want. I think just a bijection. Yeah. So a bijection is fine, I guess. So mm, let me see. Once I think the bijection is fine. We will see if it is not. So f from x to y be a continuous bijection. Then, okay, let me write in notation. Then following conditions are equivalent. Or following are equivalent. Number one, F is a homeomorphism. Number two, F is a closed map. Number three, F is an open map. So, see, this is important proposition. Why? It might not be always, possible. We will see examples when we learn compact and Hausdorff spaces. So we will see various examples that it might not be possible always to, compute inverses. It's calculative. So that this tells me, okay, if you know it is continuous and it is bijective, then just look if it is a closed map or an open map. So trust me, this will be very important. We will see when we learn compact and Hausdorff spaces, we will have a, very important theorem there, which we will use, many, many times in topological, sorry, in something called quotient spaces. Okay. So, yeah, so for that you needs to learn compact and Hausdorff spaces. Yeah. Okay. So let us prove this. So, which one you guys want me to do? Or shall I leave it to you guys? I'm sorry. Okay. Let us say do 1 implies 2. So F is a homeomorphism. What it means, this is continuous, and F inverse from y to x is also continuous. Now, so you have to show it's a closed now. So let us take a closed set. So let F contained in X be closed. Okay. So since this is closed, guys, and F inverse is continuous, so what you will get, F inverse of F is closed where? Y. So what this implies, guys, F inverse of inverse is nothing but F only. So you see, this is quite simple. Similarly, I will leave this simple set theoretic exercise for you guys. Show 2 implies 3 implies 1. It's not difficult. All of you can do this. Okay. Now finally, let's discuss some examples. Okay. So say example 1. Okay. Let me think what we can do. Okay. Show that B 0 1. So this is an open ball centered at 0 of radius 1 in Rn is homeomorphic to Rn. So see, this is a very wonderful result. So what we are saying, the open ball B01 is homeomorphic to Rn. In fact, you can show it for any open ball centered at any point of any radius. You can always show that this will be, homeomorphic to Rn. So by the way, so what is open ball? So just recall it. So this is Euclidean space, okay, I'm taking. If I don't specify any topology, it's understood. So x in Rn such that norm of x is what? Strictly less than 1, right? So let us define a map. Say, let's see. Okay, note that. Okay, let us try to define a map from say F from B 01 to R. Now listen, guys. What you will do, you will take a vector first of all, a point in ball, right? You know that norm of x is less than 1. What this implies, guys? So this implies that 1 minus norm x is bigger than 0, of course. Now what you can do is, see, you need some vector in Rn. Okay. So let's have here x. Now this 1 minus norm x. Since norm x is less than 1 and norm x is always, bigger than equal to 0. So this 1 minus norm x, this also lies between 0 and 1. And I need vectors in whole Rn. So I want to, I want to map it to a point such that norm if the norm of x is very small, then the point which I am going, it should be, comparatively large. So what we will do is we will just divide it by 1 minus norm x. Note that this is non-zero because norm x is strictly less than 1. So this is a well-defined map, first of all. Now what we have to see, its inverse. So its inverse is also not, very hard to see. So there are two ways. Either, okay, you remember how we find inverse in calculus, in real analysis? Let us find inverse like that. So let y equal to y1 up to yn belongs to Rn. Consider fx is equals to y. So x is again some vector x1 up to xn such that norm of x is less than 1. So what you will get from here, x divided by 1 minus norm x is equals to y, right? So if you expand this, what you are gonna get is this yi. See, this is some constant. So this yi is equals to xi divided by 1 minus norm of x, right? Now, how you do it, in calculus. So what you have to do? You have to find these xi's in terms of yi's, right? That's what, right? That's how you do. So note one thing. So there you have to do something. See, this is norm x here, okay? And you have to, what you are getting here is something like this only. That yi 1 minus norm x is equals to xi. But the xi, what you want to form, it should be independent of x. So how will you do that? Any idea? So you have two equations. For example, if I take I equal to 2. So what's the idea is, so okay, you have y1 equal to x1 divided by 1 minus under root x1 square plus x2 square, right? And what you have here is y2 is equals to y2 divided by x2 divided by 1 minus again x1 square plus x2 square. See, first of all, the very big problem is, can you guess what? This under root. So what we will do is, let us simplify this. So this is yi minus yi norm x is equals to xi. Now what you do is, you take this thing this side and this thing this side. So yi minus xi, okay, is equals to yi norm x. Okay. Now what you do is, you square the both side. So this under root thing will go. So if you square this, so what you are gonna get is yi minus xi whole square is equals to yi square. Then you have this thing, x1 square plus x2 square plus somewhere is xi square plus dot 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 plus what, xn square. This term you have. Now what you do, you expand this also, yi square plus xi square minus, here what you will get, 2 yi xi right? And this whole thing here. I mean, I would have, in terms of norm only, I think that would be easy. Um, okay, let us see what is more easy. So what you will have here is, so this, you have to see this coefficient of xi square. So xi square, if you take, the coefficient is what? So here it is 1, and then you will subtract this xi square here, so it will be minus yi square, right? And then what you have, this plus minus of 2yi into xi, right? Now collect all, others. So yi square, if you see, that would be 1 minus, note that 1 you have already collected with xi square. So what it would be? It is nothing but sum of j not equal to I xj square equal to 0. Now I will leave this as an exercise. Solve for xi. Okay, this is just quadratic equation. So what you will get finally is when you club everything together, you will get that x is nothing but y divided by 1 plus norm y. Please verify. That's what you are gonna get finally. So now, so what will be your map? So your map from, say, F inverse will be from where to where? So by the way, I directly started, computing inverse of it. So I will leave this as an exercise, show that it is 1, 1. F is 1, 1. By the way, F is continuous. This is just real analysis, calculus on Rn. So what is F inverse? F inverse is from where to where? F inverse is from this, Mm, now we are in Rn, and we are going to ball 0, 1. F inverse of, say, x, this is nothing but x divided by 1 plus norm x. So if you want to by chance say compute the norm of this will be norm x divided by 1 plus norm x, and 1 plus norm x is bigger than norm x, right? So this is less than 1. So it is actually inside the ball 0, 1. And this is also a continuous function, right? This is just calculus and Rn. So you see, f and f inverse are continuous. And this is how you compute inverse. I'm not, solving the whole thing. You guys can easily solve. It's not very difficult. You just have to write things properly. Okay, please do write things properly, and you will get very simple and sober form. It will not be anything, which is so troubling. Okay, so let us proceed. So example 2. This is one of the very, very, very important example. This is called stereographic projection. It is very important. One importance you will realize when you will study one point compactification. We will come to it, but yeah, after a long time. It's not like too frequent. Yeah, we need some time. So stereographic projection. So let us understand, what is this stereographic projection? So this we can do for, any dimension, but let me fix up to like this setting. I have a sphere. Okay. And let's say I'm placing it like this. So say this is my R2 and this is what? S2. Okay. I'm placing like this. So this is in R3 same. So let's say decide the coordinates also. So this will be 0, 0, 0. Okay. So I'm just, making some sphere. So let us take its radius as 1. So what will be this point, guys? So this is, say, your z-axis is like this. So what is this middle point? I mean, here this is the origin, and let's say you are going, say, 1 unit up. So you may say, oh, this is not S2 exactly. You are shifting it up below or above, whatever. So for you, I can make an exception. So let us see, take this R2, I'm taking at this level. So say this is the point 0, 0, -1. Now this is origin and say this is, although it doesn't matter. This is 0, 0, 1, which we'll call North Pole. Okay? I want you to observe one thing. So take any point on sphere. Say take here. Now, from North Pole, join this point and emit this ray and passes through the R2. So it would be somewhere like here. So if you have observed, this is the point on sphere, okay? It's just S2, okay? So this point, when I pass like this, so it will cut a unique point here, right? On R2. Or if this is not a very good representation for you, let me do like this. Let's take a point in this. So if you take any point, say here, join this, emit this ray to R. Yeah. So this is your point, huh? Array, oh my god. Yeah. So yeah, a little bit here and there, huh? So you will get a unique point here, right? On R2. Similarly, if you take a point on R2, say this, join with the North Pole. So it's coming from inside, then it comes on this point to the sphere, and then it goes like this, right? So if you see, like say from outside, like you imagine it, you take a ball, Costco ball or plastic ball, and try to take a long needle, very long needle, and try to insert it like this, and you will see from North Pole it will cut exactly 1 point on sphere and go to 1 point on R2. And similarly, from R2, when you join North Pole, you exactly get one intersection point of this ray connected with North Pole on the sphere other than North Pole. So what this tells me, there is a bijection between S2 minus this North Pole and R2. What we will prove is this is not just a bijection, this is also a homeomorphism, meaning it is continuous and its inverse is also continuous. So let us, formally now define the maps. So say you take a point on sphere. So let x1, x2, x3 belongs to where? S2. Okay. For a moment, when you take this point here and you have already this North Pole, right? 0, 0, 1. What will be the line segment which emits, or the ray which emits from 0, 0, 1 and passes through this point x1, x2, x3? It would be 1 minus t, right? 0, 0, 1 plus t x1, x2, x3, right? Where this t is bigger than or equal to 0. So at 0, it's just your North Pole. And when you passes, it is continuing like the ray, which we have shown in green color in the above picture. Right? What you are interested in? You are interested in when it is hitting R2. See, this is a R2 sitting inside R3. So R2 you can look like this. X1, X2, 0. Some point like this, right? And this is how. So this is how R2 looks inside R3. In fact, you can prove this if you let it A. I will give you an exercise. This is a simple one. Exercise. Show A is nothing but A is homeomorphic to R2. So A is a subset of R3 which is homeomorphic to R2. Okay. Now, so we are interested in when the third component is 0. So let us properly solve this and write the components properly. So first component would be tx1. Second component would be tx2. And third component would be 1 minus t plus tx3. T is bigger than or equal to 0. When this ray will hit my R2? When the third component is 0. Meaning, what is the meaning? This implies 1 minus t plus tx3. This is what? 0. Right? That's what you have. No? I hope this is clear. Okay, so what you are getting here is, so if you solve this for t, what you will get? So 1 minus t plus tx3. I'm bad in calculations. So this implies 1. Say let's take t common. x3 minus 1 is equals to 0. So this is, let's say, take this side. So t1 minus x3. And what is your t? This implies t is equals to 1 divided by 1 minus x3. Is it fine, guys? So that's how your t should be. Now you can clearly see the map, right? So what you will define, f from S2 minus your north pole. By the way, why we are subtracting this north pole? If you emit a ray from the north pole and hit the north pole, where will it touch R2 anywhere? No. So that is what stereographic projection is. You know where it's applied in geography to make maps. Now we have technology. Imagine the time when those old people used to do. How smart they were. Okay. So what we have is to R2 f of, I'm sorry, x1, x2, x3 goes to where, guys? x1 divided by 1 minus x3, x2 divided by 1 minus x3. You haven't asked, what if x3 can be 1? Can x3 be 1? Tell me. Think about it. It cannot be. That's how we have chosen the, points. We are removing the North Pole. Only possibility is that where it is, you know, 1. Right? It's just the 1 point. So since x1, x2, x3 is not equal to, I have written here minus North Pole. Yeah. So I have written there my n equal to this, but yeah, I haven't written. Take a point there. Okay. So this is not equal to 0, 0, 1. So x3 is not 1. On sphere, there is only one point where x3 is 1. That is 0, 0, 1. So that is your map. Now you don't worry about the second component. So similarly, I ask you to do an exercise. Generalize this to, sorry, this to f from Sn minus n to Rn. Now, note that f is continuous. See, R square has the product topology. The projections are continuous, so this is continuous. And this you can show easily. I'm not going to prove that this is continuous because this is something you have learned in calculus. If not, it's the time to learn. That's all. Okay, good. Now, let us have that picture again, huh? Because we need it. This picture. Or just look at this picture. Now we want to construct, you know, what we want to construct? A map from R2 to S2. So what we will begin with? We will begin a point here. x1, x2, 0. And then we will consider this line segment and see where it is intersecting, right? That's the precisely point I want. Okay, good. So let us define G from R2 to S2 minus N. So to do that, let us take a point x1, x2, 0. This x1, x2, let's take x1, x2, we will identify it by x1, x2 in R2. So this is represented or identified by x1, x2. By identified means, see you have a homeomorphism I told you between R2 and that subspace capital A. That's what. Okay, so now consider the line segment again. So begin from x1, x2, 0. And now you don't need to go beyond n. So just consider till n. Till sorry, 0, 1. What you have to look, Of course, this intersect at the North Pole, N. But you have to look is this middle, this point. What is this? So for this point, what you have all points on this line segment. It should just satisfy the equation of sphere, that point. So what is it? If you square the components and sum it, it should be 1. So that is, we want t such that 1 minus t. Let us solve this again. So this is 1 minus t x1, 1 minus t x2, and t, right? T in 0, 1. So what you want? You want to square it. And then this sum should be 1, right? That's what you are interested in. And such t you want to find. So let us find out this t, okay? I mean, there can be other simple ways or simple calculation, but yeah, this is one way to do that. So, okay, so what you have is, you have this 1 plus t square minus 2t x1 square plus x2 square, right? That's what you have, plus t square equal to 1. Now collect the powers. So t square, how much you have with t square? So first of all, you have x1 square plus x2 square. Then you have this minus 1, right? That's all. Let us see what you have with t. So with t you have, what you have? Minus 2 x1 square plus x2 square, right? Is it? That's all? Right? Now, the constant term. You have 1 here, just keep it this side. So already you have this x1 square plus x2 square minus 1. I hope I am not making any mistake. Let us denote this norm of x square is x1 square plus x2 square, right? So we'll just write it for the simplicity. Norm x square minus 1 t square plus t minus 2 norm x square plus norm x square minus 1 equal to 0. Right? Any questions? I hope this is fine. Good. Let us find the value of t. So similar to, something like this above calculation is there in the first example. I will not do that, but I will do this properly. So, now you can do that also. I'm again saying there might be simple way, but let me do this way. So, okay. So what you have, t is equals to minus, what is the formula? Minus b. So 2 norm x square plus minus under root b square, 2 to 4 norm x4 b square minus 4ac. So 4, this whole thing, right? A and c. 4 plus 1 minus 2 norm x, right? Square. Divided by twice of norm x square minus 1, right? Now let us solve this. So this looks complicated, but it's not that complicated. Just let's solve it. Plus minus. See what is this? 4 norm x4 minus 4 norm x4. Gone, see? And then what you have? This is Just a second. 4AC. So something, no, this is fine. 4. Some mistake I might have done, guys. Let me see. So this is, yeah. So let's, I should have put here only, norm x square. So norm x square plus norm x square t square minus 2t norm x square. What else? Plus t square. So this is plus t square, right? Can you see what is my mistake? This should be plus. This should be plus. And now let us change this. So you see, these silly mistakes happen sometimes. It's not a very big deal, right? I mean, if you may think it is, but it's not very big deal. So for AB, so this is norm x4 minus 1. So that's all. So this is plus 4. Now it, see, it become nice. So what you will have? 2 norm x square minus 1. So what you are getting here is t equal to 2 and 2 will cancel out. This is root 4 only. So norm x square plus minus 1 divided by norm x square minus 1. So this implies t is 1 or norm x square plus 1 divided by norm x square minus 1. Can t be 1? Look at the situation. Where is t? See, if t is 1, then I'm getting North Pole. Definitely you will have two solutions. Na? There are two possibilities of t when we square it and sum it, the each component, because we are looking at the points which lie on sphere, right? So I don't want North Pole because North Pole is removed out of the equation. So this implies t has to be right. So this is your t. So let's, finally put it back. So what is my point? So 1 minus t, and then there is t. Okay. So what is 1 minus t? Let us compute that also. What will be 1 minus t, guys? Norm x square minus 1 minus norm x square minus 1, right? Like this only, no? Divided by norm x square minus 1. So this is this and this will go. So this is 2 divided by 1 minus norm x square. Something like this, right? So this is your 1 minus t. So what map you are getting is, so G from R2 to S2 minus North Pole is nothing but G of x1 comma x2. So you are calling this vector x is nothing but 1 minus t. So t1 minus into x1, 2 by 1 minus norm x square into x2. And what you have? T. I think there was t, right? So this is, yeah, plus 1 divided by norm x square minus 1. So this is, the whole thing you have. Okay. I hope I haven't done any mistake. Yeah, I have done one mistake now. Oh my God. This I haven't corrected. This should be plus. This should be plus. I'm sorry. So what you will get is, okay, let's change the signs. So this is minus, this is plus, this is minus, this is plus. And this is, you see why I get this mistake. So if you have noticed what I have written this so norm x square minus 1, but norm x can be 1, right? So it means what I have defined, my map has some defect. So that's why I corrected my mistake. And I noticed, okay, something is wrong. So, okay, so 1 minus 3, so norm x plus 1 minus this plus 1. So 2 by, yeah, this, this, and above is minus 1. Now it is perfect, right? So that's what you have to do. So this is your map G. Again an exercise, generalize this from your G to say some Rn to Sn minus the north pole. And this is a continuous function. So you see what we have shown? We have shown that Rn is homeomorphic to Sn minus n for every n. So this is very important. Very, 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 very important. So I hope this much is fine for today. I just wanted to give you one example to try. So show that. Let me see. F from 0 to 2 pi to S1. F of t is e to the power it. Yeah, this only. 1 continuous. Number 2 1 1. Number 3 is not an open map. We'll come to open map and closed map maybe sometime later when we discuss compactness, Hausdorffness, and about quotient topology. I mean, there can be many more examples. So like I always say, the usual books you refer, Introduction to Topology by Tej Bahadur Singh. It's a very beautiful book and it's not well known. So it's Springer or, your standard Mancrace. So in next session, okay, I have to think what I'm planning to discuss. Okay, maybe we will discuss this connectedness and then compactness and all because and yeah, many more things are there. Maybe we will start with connectedness. I will, stop here with the example. Okay, let me give you one more fun exercise. So let x be uncountable set with cofinite topology. Show that f from x to r is continuous if and only if f is constant. So one way is obvious, very easy. If f is constant, you have to show that it is continuous, but the other you have to think. Okay, and one more problem, then I will definitely stop. This is also very nice and important. Check. See, you have x tau 1, x tau 2. same space, two topologies, and you have this identity map. What it does? It's identity map, sends small x to small x. So check, find conditions on tau 1 and tau 2 such that number 1, identity is continuous, and number 2, identity map is a homeomorphism. So your misconception always is not true. Identity map need not be continuous. I may have given this example earlier. So I think this is sufficient for this lecture. Let me stop, and so we will probably discuss about connectedness next time. Probably I will see if there is anything else I want to tell. Thank you very much for your attention.